Hi everybody, welcome to another video in Calculus 1, section 4.4, graphing functions. So in this section we combine what we learned in section 4.1 and 4.2 and pretty much everything we learned before that in Gaussian algebra, trigonometry, recalc. Put all of them together and to graph a function. So this is pretty much everything we can do to affect the and graph the function. So, because the first step is identify the domain that we will graph the function. Right, so that is not the range, just the domain. Now we can test the symmetry. So an even function is when f is negative x is the same as f of x. An odd function is f of negative x is negative f of x. The reason we do that is so that we can determine the symmetry. The even function is symmetric with respect to the y-axis. An odd function is symmetric with respect to the origin. Right. And now the most important that we've learned in this section at this step. The first derivative equal to 0 does not exist. Potentially we have the critical points. So the critical points of course must be in the domain. So that's why we say it is potentially. We still need to make sure that those points belong to the domain. If it is, it will be a critical point. And then second derivative equal to 0 does not exist. Once again, potentially is an inflection point because it may or may not be an inflection point. And then we will test derivative. Positive, it is increasing. Negative, it is decreasing. For second derivative, positive is concave up, negative concave down. And after that we determine any local maximum, local minimum, and then inflection points. And those are what we can get from the derivative. And of course what we have from the previous chapter, the asymptotes, vertical asymptote and horizontal asymptote. The intercept is more like in Gaussian algebra, where x-intercept is when y equal to 0, and 1 of the y-intercept is when x equal to 0. And then we combine all of them, we graph the function. So actually our focus is only on the step when we do the first and second derivative test. And if there is any vertical or horizontal asymptote, we can determine that as well. But our focus, of course, is on the derivative. Right. Now let's see how that works. Now, given the following function with the first and second derivative, which is continuous, summarize the information using a number line and then sketch a possible graph. Actually, we just sketch the graph and then try to put them together. Just try to see. Right. Now, let's look at this. First, if the derivative is positive, that means the function is increasing, right? And then the second derivative is positive. That means it's concave up. So think about this. We have an increasing function. Okay. More like this. It is increasing function, so it's going up. And then they have to concave up, so we have to bend the end up. So the graph is going to be like that. So put them together from negative infinity to 0. It's going to go up like this. Right, next, derivative is negative, so that is decreasing. It is positive on the second derivative, meaning it's going to be concave up. So originally we have a function that is decreasing because derivative is negative. And then, but it is concave up, so we're going to bend that. So we'll be up. So the graph for that part is going to be like that. And the same thing for the other. Derivative is positive, going up. Second derivative is negative, concave down. So originally it is concave up, it's positive, increasing. But then we have to bend the end so that it will be concave down. So think about this. Originally it is the tangent line and the function like that, and the line, and then we're going to bend so that the tangent line is above the graph, so it will be increasing but concave down. Now this one derivative is negative, that's going down, and second derivative negative, so it's concave down. So originally it's going down, and then we have to bend it below the tangent line. So the graph will look like this. And then when we put them together, in the graph, so first we know that from negative infinity to 0, it is increasing and concave up. So it will go, we did not know much about function, but we know it's going to go up to this point. After that, from 0 to 2, it goes like this. So just copy and paste that portion of the graph. After that, from 2 to 5, increasing and concave down. And then from 5 to infinity, decreasing and concave down. So as you see, so knowing the first and derivative, we can know the shape of the graph, and then we just piece by piece put them together, and that's what we have. Right. Now let's look at this graph. Now let's try to graph this example. Graph, this is a polynomial function, so it is continuous and defined everywhere. So if we have to write the domain is all real numbers because it is defined everywhere. Right. But like I said, our focus here is the first and derivative and what can we get from them. While we're doing that, we might see that we might have asymptotes there, but like I said, focus on the derivative. So first, let's do the first derivative. So we check the derivative. So that gives us 6x squared minus 6x minus 12, right? And then when we have derivative, we let them equal to 0, they not exist. Potentially we will find the critical points, and then of course we test to see where's positive, where's negative. But the sign chart, we're going to do that later. This section we do a little bit different, but still have the first derivative equal to 0, and the first derivative does not exist. We know that does not exist, we will not have anything, because the function or derivative is continuous everywhere. I mean defined everywhere. Right. Now we'll take the derivative equal to 0. Divide both sides by 6. And this we can factor out. X multiply minus 2, x plus 1. Right, so this gives us x equal to x minus 2 equal to 0, x plus 1 equal to 0, so we have x equal to 0, and x equal to 2, and x equal to negative 1. Right, so that's what we have for the first derivative. Let's find the point. So let's find the values at f of x when x equal to 2 and x equal to negative 1. Put it back in the original function. Right, 2x cubed minus 3x squared minus 12x plus 1. Let's go to the table. Right, x equal to 2 is negative 19, and f equal to x equal to negative 1, y equal to 8. So we have right. Right, so we just write out the points. Don't do the sign. I won't do the sign chart yet. I'll get back to that in a minute. So that's what we have for the first derivative. Now we'll go to the second derivative. I'll take the second derivative. That equal to derivative of the first derivative give us 12x minus 6. Derivative of negative 12 0. So that is the second derivative, and then we will let the second derivative equal to 0 and does not exist. For the same reason, we do not have anything here, because the derivative is defined everywhere. Right, now we take derivative equal to 0. So in this case we have x, 12x equal to 6, or x equal to 1/2. Now let's just try to find the values of the function at x equal to 1/2. Notice that I put in the original function. So the table doesn't work because I don't have 1/2. So in that case, go to second trace. sorry, just hit trace, and then just enter the x values 0.5, that is 116. Okay, trace 0.5, enter, right, negative 5.5. Right. Of course, you say we already have the graph. Why do we have to do all of this? Well, in this case, we have all the characteristics of the graph. We know exactly where the maximum and where the minimum potentially is, and then we know the inflection point. But of course, we haven't done any sign chart. And now we do. Now we go to the sign chart. Just one step. Now it's step number 3 is the sign chart. Right, this sign chart will contain both the derivatives the domain of the problem. All real numbers, so negative infinity to infinity. We have the whole number line here. Right. Now we have x. The first derivative is that second derivative is 12x minus 6. Right, now remember we put both of them together. Now let's look at the first derivative. First derivative equal to 0 or does not exist. We have x equal to 2 and x equal to negative 1. So those are the 2 points we have. And for the first derivative equal to 0 or does not exist, we have 1/2. So I'm going to put those 3 points in here. Negative 1, (1/2), and then 2. Yeah, so negative 1 and 2 come from the derivative, and 1/2 come from the second derivative. And when x equal to negative 1, the derivative equal to 0, derivative equal to 0. And when x equal to 1/2, the second derivative equal to 0. So those are the partition numbers for the first and the second derivative, because we will make the table. We will use the test point and then test the first derivative and second derivative. So let's pick the point between the intervals. We can choose negative 2 here, negative 1 and 1/2. How about 0, 1/2 and 2, 1, 2 to infinity, 3. Right. So for this, usually I can just put in the table. Hit stat, and if there's anything in that, highlight the list, highlight that. Never hit the delete key here, never hit that, just hit clear. Clear the list. If you accidentally hit delete on the L, then it disappears. Then we have to rename it by second L1, and here second L2, and then so forth. Yeah. Right. Now we have the points. -2, 0, 1, and 3. Those are the test points. I'm going to put in the derivative. So I will highlight that, and this is the derivative. 6, instead of x, I will use L1 minus 6 x minus 12, and we have the values. Again, this is the sign chart, so the sign is all we need: positive, negative, negative, and positive. Besides, those are the test points we choose, so it doesn't have any significance in the graph. The significant point on the graph are those. Right, and then for L3, do the same thing. For the second derivative, will be 12 L1 for x, second one L1 for x minus 6, and we have those. So will be negative, negative, positive, and positive. Right, and then put them together. Right. Sorry, I might not see. Hopefully we have that. Right, so that is sign chart. Now, graph, in terms of graph, there are only 4 possibilities. This is increasing and concave up, increasing and concave down, decreasing and concave up, decreasing and concave down. Now we just choose the right one for each one of the interval. Now, this one, positive, increasing, and then negative on the second derivative, concave down. So the first part is going to go like this. The second part, negative, decreasing, and then concave down. So we have to bend it down. And then negative, decreasing, but it is concave up, so we bend it up. And then positive, increasing, and then bend it up for concave up. Right. Now in terms of points, if we go up and down like this, of course this is the local max, right? Of course I'm just going to write maximum because we know that it is local max. And the point when x equal to -1, we did earlier, it is 8. So we say max at -1 when x equal to 8, or y equal to 8. Now, at this point, the second derivative change signs. So this will be the inflection point. Because it goes from concave down to concave up, so we have the inflection point there. Inflection point. And that when x equal to 1/2, y equal to -5.5, or -11/2. And when x equal to 2, look like this will be a local mean. And when x equal to 2, y equal to negative 19. So those are all the information we get from the first and second derivative. Now put on the graph, and we just copy and paste this portion of the graph into the graph itself. So let's see, we have negative 1. Actually, because the scale we can choose. So let's say negative 1 is here, and 2 is there. 1/2 will be here. And then the points. Negative 1, since we go to 19, so let's choose each one of them is 4. So 4, 8, 12, 16, and then so on. So we have negative 1 and 8. Negative 1 and 8. So the first one is going to be here, negative 1 and 8. Next, 1/2 and negative 11 over 2, so negative 5.5. So about here. And then, sorry, negative 1 and 8 should be here. So, negative 1 and 8, 1/2 negative 5.5, and then 19, so 4, 8, 12, 16, 20, so it's about here. So, and then we just copy and paste first that portion. Of course, if we let this equal to 0, we will find the x-intercept, so we know more points on the x-axis to do that. But like I said, the focus here is on the derivative only, so it's going to be that part. And then from negative 1 to 1/2, it's going to be this portion. Just copy and paste. So it's look like this. And then 1/2 to 2, this, and then 2 to infinity. So put them together, we have this graph. Once again, we can find the x-intercept, so we know where it actually intercepts the x-axis, and we can find the y-intercept, so we know exactly where it intercepts here. But like I said, of course, it's obvious if the more points we have, the better the graph is. But like I said, the focus here is only on the derivatives and the second derivative. So here we have the local max. And this is negative 1 and 8, a local mean, negative 2 and negative 19. And then we have the inflection point. It's 1/2 and negative 5.5, or just say it. Inflection point as 0.5, negative 5.5. Right, so that's what we get from the first and the second derivative. And that's all we do. More samples. Right. Let's graph this function. So first thing we look at this one. If we have to find the domain, x cannot be equal to 0 because divided by 0 is undefined. So we have to pay attention on that. And then we just focus on the first and the second derivative. So first derivative. we'll take the first derivative. Based on that, it will be x plus 4 x to negative 1. And we use the pound rule. So x equal derivative of x is 1. And take the negative 1 down, negative 4 x to negative 2. Right, so that is the derivative, right? However, since we're going to have to let that equal to 0 and unify, so we have to solve for that later on. So I will rewrite this as one big fraction. So this is easy to solve for. X to negative 2 bring down, become x squared. Now, common denominator, I can multiply x squared top and bottom. And minus 4 over x squared. I put them together. We have x squared on the top. Minus 4 over x squared. So that is the derivative. And now we let that equal to 0, does not exist. Equal to 0, derivative does not exist. Right. Now, derivative equal to 0, if we have a fraction, one big fraction, then we translate. That means the top is equal to 0. If we have the fraction when it does not exist, meaning that the bottom equal to 0. And you say, what happened if both of them equal to 0? Well, if both of them equal to 0, we should be able to simplify something. Right, so x squared minus 4 equal to 0. Move the 4 over. X squared equal to 4. Take the square root on both sides. Be mindful with that. When you do that, there's a plus or minus. So we have x equal to plus or minus square root of 4, which is 2. So if x equal to 2 or x equal to negative 2. Now, when the derivative does not exist, meaning the bottom equal to 0. And once again, we take the square root on both sides. Give us x equal to 0. Plus or minus 0, still 0. Right, now let's test them. At x equal to negative 2, f of negative 2 equal to, actually we should put in the table. For this it will look better, but let's just write this out. Right, now I have the function x plus 4 over x, and then hit trace when x equal to negative 2, it is negative 4. At x equal to 2, f of 2 is equal to 4. And at x equal to 0, f of 0, it didn't give us anything, meaning it's undefined. So the point is undefined into the function, meaning that there might be a gap in the function. It may or may not be the asymptotes. Alright, so we back to that later. But what we have for the derivative is that. Now, second derivative. Right. Second derivative is the derivative of the derivative. So we already took the first derivative. Sorry, this is the derivative. Now we'll take the second derivative. Second derivative is the derivative of the derivative, so I can choose any of this. And this one look like it's easy to take derivative. Derivative of 1 is 0. Derivative of that gives us 8 x to negative 3, which is 8 over x cubed. Right. So that is the second derivative. Of course, and then I will let that equal to 0. Or does not exist. Equal to 0. The top is equal to 0 because we have a fraction here. Does not exist, meaning the bottom is 0. So 8 equal to 0, of course there's no solution here, so we don't have anything over here. And does not exist when the bottom equal to 0. X cubed equal to 0. When we take a cube root on both sides, there's no plus or minus. Only put plus or minus on an even root. If it is even root, square root, fourth root, there will be plus or minus. If it is an odd root, there's no plus or minus, so we have x equal to 0. And then at x equal to 0, we already did this. The function is undefined. Right, so we have the first and second derivative. Now put them together in the sign chart. Right, that will be good enough. Right. X. This problem, did not specify the domain, so we go from negative infinity to infinity. And then we have derivative. Yeah, we can choose any of this. Yeah, just keep the first one. We can choose any of this as the derivative. Because you can choose that. I just put the first one. And then the second derivative. Again, we can choose any of this. We can just choose 8x to negative 3. Right. When the derivative equal to 0 or does not exist, what do we have as x equal to 2, x equal to negative 2 when the derivative equal to 0, and x equal to 0 when the derivative does not exist. So we will have negative 2, 0, and 2. And in particular, when x equal to negative 2, the derivative equal to 0, and equal to 0, the derivative does not exist. On the second derivative equal to 0, we don't have anything, but does not exist, we do have 1. So x equal to 0, so that also 0, and that also does not exist. Right, so with that we divide that and we have a table. Now let's put them in the derivative and second derivative, so we have the sign chart. So test point between this negative infinity and negative 2, I choose negative 3, negative 1 between negative 2 and 0, 1 between 0 and 2, and 3 between 2 and infinity. Right, so that, let's go to the table. Hit stat, edit. Of course, if not, we can just put the numbers in here and do that by hand. That's perfectly fine. Clear the list. It will be negative 3, negative 1, 1, and 3. L2, let's clear that, is equal to 1 minus 4. List 1, 4. L1, have to hit second number 1 to the power of negative 2. If you want to be safe, negative 2. Right, look like positive, negative, negative, positive. Positive for negative 3, negative for negative 1, negative for 1, and positive for 3. Right. Second derivative. Clear that will be 8. The list to the negative 3. Yeah, we have to enter this when we highlight the list L2 or L3. So it will calculate for the whole list. Negative, negative, positive, and positive. And then just do this. Increasing and concave down. Decreasing and concave down. Decreasing and concave up. Increasing and concave up. So we're going to bend it up. Right, so that's what we have. Now, if the graph goes like this, and actually we do have the point here, when x equal to negative 2, y equal to negative 4. So in this case, we have the maximum here. because the function is defined. And it goes like this. It must be a maximum. Maximum will be when x equal to -2, y equal to -4. And when it goes like this, and the function is defined when x equal to 2, y equal to 4, so we do have the minimum here. X equal to 2, y equal to 4. And when x equal to 0, it is undefined. So if it's undefined, we will test if potentially if it is an asymptote or not. So it is the vertical asymptote, right? Because if the point happen in the middle, it cannot be the horizontal asymptote. Horizontal asymptote will be on the end though. So if we want to, we can test for the asymptotes. And only at x equal to 0, because we know x equal to 0 is undefined. We don't know if it is just a gap. It could be just like this when there's a gap and it's undefined. Or it might be approaching to the line for the vertical asymptote, so we don't know that. So we take the limit as x goes to 0 for the function. Right, so if we do that, put in 0, of course 4 over 0 like this is not going to work, right? So in that case, have to consider the one-sided limit. So let's say we look at the left-hand side of 0. Now, for a finite number divided by something that goes to 0, so what do we have here? So that's going to be 0, and then 4 divided by something that goes to 0, so this will be negative infinity. And of course we can do the same thing for the limit when x goes to 0 from the right hand side. One of this is enough to say it is an asymptote. And a finite, there's a constant divided by something that goes to 0, so this is positive infinity. So x equal to 0 is a vertical asymptote. So just check the limit. When x goes to that point where the point where the function is undefined, find the limit for that. If the limit goes to infinity, either one side, then we have the vertical asymptote. Right. So we know we have the vertical asymptote at x equal to 0. So next. Let's plot on the points. The maximum, -2 and -4, -2 and -4. We know it's maximum, right? So it's maximum. We know it's maximum, so it have to be below this. So that's why I write that on the top. And then at 2 and 4, we know this is the minimum, so we know that it's not going to get any lower than this. So that's why we write below it. And equal to 0, we have the asymptotes. And then just copy and paste the portion here, the portion of the graph. It will approach to this line. Oh, it goes down like this, and then on the other side, same thing. just copy that portion to the graph. One thing we haven't mentioned on this one, when x go to infinity, what happened when x go to infinity? We're trying to find if there is any horizontal asymptote. If we let x go to infinity, then we have infinity here, and then 4 over infinity will be 0. So when x go to infinity, the function go to infinity. So that's why we have no horizontal asymptote. However, when x go to 0, we approach it to this function. So in this problem, actually we have is the slant asymptote. So actually we should do this first. So the graph actually, this is not as good. The graph actually will approach into that asymptote. Right. Of course, that's not important, but I just want to make it precise. So I will write this as x goes to plus or minus infinity. The function is equal to x plus 4 over x, right? Now when x go to plus or minus infinity, this one go to 0. So the function approaching to y equal to x. So that's why in this case we have the slant asymptote of y equal to x. So the graph of the function approaching to that line. We don't need that, but yeah, if we didn't know that, we just know that the function will look like that. Will be good enough. And there's no inflection point. Because if this point is undefined, so there's no inflection point. There's only a local max and a local mean. Right. Whether we have the asymptote, the slant asymptote or not, is not it's the focus of what we do here. Right. So that's what we have in that problem. Right, so first derivative, second derivative, put all of that in the sign chart, and we know the graph will have to be one of those four. Sorry, one of those four, and then we can just copy and paste the portion, and then we have the graph. Right, copy that here. Yeah. Now let's graph this. Right, on this one, we already graph on -1 to 2, so we are given the domain, so we have to be mindful of that. First, let's do the first derivative. Right, so that is a function. Let me rewrite the function. Yeah, I can multiply it out. That gives us 2 x to the 2/3. And then x to the 2/3 times x. When we multiply them, we combine the exponent. By default, the exponent is to the first power. So that gives us minus x to the 5/3. Right, so that's what we have. Sorry, I have to pause the video to refill the ink. Right. So we take the derivative of that. So we have 2. And then take down the power, so 2/3. Original power minus 1. 2/3 minus 1 minus 1 over 3. Right? And then same thing here. Take down the power. And then original power minus 1. 5/3 minus 1 is 2/3. So this will be equal to 4 over 3 x to the negative 1/3. I will move to the bottom and turn to positive, and then minus 5/3. The x to 2/3 is positive, will stay on the top. Right. Now, since we will let that equal to 0, does not exist, it would be nice if we have that as one big fraction. So in that case, I can multiply top and bottom to that term to get the same common denominator. The bottom common denominator of 3x to the 1/3. And the top we have 4 minus 5 times x to 2/3 times x to 1/3 combined, the same basis, we combine the exponent 1/3 and 2/3, so that's just 1, or just 5x. So that is the derivative. Right? Now, derivative equal to 0. Derivative does not exist. We have a fraction, so derivative equal to 0, meaning the top is 0. Does not exist where the bottom is 0. So 4 minus 5x on the top equal to 0. So solve for x. Negative 5x is negative 4. Or x is negative, it's going to be 4/5. And that certainly is between negative 1 and 2. So that's good. The bottom equal to 0. 3x to 1/3 equal to 0. So x to the 1/3 equal to 0. Of course, we keep both sides, so x equal to 0. That gives us 0. 0 cubed still 0. Now let's test them. Need to evaluate the function. X to the 2/3 times 2 minus x. It trace. Of course, I gave you the graph already. I know that, but the point is, of course, we're not just focused on the graph. We need to know exactly where the maximum, minimum. The graph, even though it looks like there's a maximum there, but we have to find the point algebraically. Not by the graph. So x equal to 0, y 0, x equal to 4/5. So 0.8 and 1.03 something. So when x equal to 0.8, y is about 1.03. Since we graph, we can just get some decimal number. And when x equal to 0, when x equal to 0, we did that earlier, and that is 0. Yeah, put 0 on here. That should be 0. Right. So that is the first derivative. Now second derivative. So we have the first derivative, any of that will do, then we take the derivative. Of course we can use the quotient rule, but that looks complicated. So can we use any of this? It's not ideal. Actually what I should have write earlier is the derivative here. I can just, this should be just, now let's focus on that. If I just write equal to 4 over 3 x to the negative 1/3 minus 5 over 3 x to the 2/3 will be much better, right? Will be much better to take the derivative from here. It's not easy to solve for, but at least this is easy to go from there and go to the second derivative. So I will say the first derivative might be better to write in this form. So when we take the derivative, it will be easier. Second derivative be 4/3. Take down the power, original power minus 1. Minus 5/3. Take down the power, original power minus 1. So multiply this, we have negative 4 over 9 x to negative 4/3 negative 10 over 9 x to the negative 1/3. Right. And then of course we can move the negative power to the bottom. Of course here we can factor also, but I will do that as a fraction. Once again, we have to get to the common denominator, so we have to multiply x to the 1/3, top and bottom. So that gives us negative 4 on top. The bottom though, 9x to the 1/3, and then multiply straight across. Sorry, not x to the 1/3, just multiply by x. X to the first. Because when we multiply x to the first, 4 1/3 plus 1 is 4/3. So x to the 4/3. 9x to the 4 over 3 is the common denominator. So multiply x top and bottom. So that gives us x to the 4/3. X to the 4/3. Right. Minus 10x. Right. That's what we have. Right. And then equal to 0 does not exist. Right, equal to 0. When we have a fraction, that means the top is 0. So that means negative 4 minus 10x equal to 0. And then so for x, negative 10x equal to 4. Divide that, negative 10 on both sides, x equal to negative 4 over 10, or negative 0.4. and that goes between -1 and 2. And then the second derivative equal to 0. Divide both sides by 9, x to the 4/3 equal to 0. So of course here we can just say anything raised to a power that equal to 0. The only thing that happens is when x, the base, is equal to 0. Right. Once again, we will evaluate the function at this point. So we have that function ready. Trace -0.4. So it is 1.3. And we already did this at x equal to 0. The values of the function at 0 is 0. Now put all of that in a sign chart. So in this form, we already go from -1 to 2. So we're not going to put the whole number line there. Right. We have the derivative. I will write the derivative in that form. So 4/3 x to 1/3 -1/3 minus 5/3 x to the 2/3. Yeah, so that is the derivative. And then second derivative, of course I can't write any of this, but I'm going to write this one. -4/9 x to the -4/3 minus 10/9 x to -1/3. Yeah, so that is the second derivative. That is the first derivative. Right, for the first derivative, what point do we have? 4/5 and 0. When x equal to 0, the derivative does not exist. When x equal to 4/5, the derivative equal to 0. For second derivative, so I think through this. Let's move this up a little bit. Because the scale here is not really matter. Right, the second derivative, we have -0.4 and then 0. So and with that the case, the second derivative equal to 0. When it is equal to 0, the second derivative does not exist. Right, now test point. Start, and I'll go to the list. Let's clear this list. Now pick the numbers. I can choose a number between here, so that's like negative 0.7. Between here, 0.2. Between here, so that is 0.8. Let's choose 0.4. And then let's choose 1. So those are the numbers. Negative 0.7. Negative 0.2. 0.4. 1. Right. Go here for the first derivative, highlight that. Clear the list first. Now, enter the derivative. Be that 4 over 3 x. Don't enter x, use L1 for x. To the negative 1/3. Minus 5/3. The list. Five-thirds. The list to the power 2/3. Of course, you have to highlight the list when you enter it. That's why it will give an error. Right. One more time. 4/3. Yeah, have to highlight the list when we enter this. Right, so we have the numbers. Negative, negative, positive, and negative. Right. And then go to the second derivative. Let's clear that first. Highlight that and enter the second derivative. Negative 4 over 9. The least 1 to the power of negative 4 over 3. Negative 10 over 9. L1 to the power of negative 1 over 3. So I will have positive, negative, negative, and then negative. Right. And then just do the curve. It's decreasing but concave up. And then this decreasing and concave down. Increasing but concave down. And decreasing and concave down. Right, this point definitely is not going to be anything, cannot be anything here. It's not max or min, that's what I mean. Here, if you go like this, and if the function is defined, that will be the maximum for sure. And when x equal to 0.8, y equal to 1.03. Now, if it is at this point, this should be the minimum. If it is defined, and indeed it is defined when x equal to 0, y equal to 0. So this is, we have the minimum here, because when the graph goes like this, it have to be the lowest point, which is 0, 0 mean. Now, on the second derivative, the sign changes. So it change concavity from concave up to down. So there should be an inflection point here. Inflection point, and when x equal to negative 0.4, y will be equal to 1.3. So that is inflection point. So let's graph, put all of that on the graph. The graph only go from negative 1 to 2, so we choose the scale, so we can graph better. Let's see, 1, 2, 3, 4, 5, 6, 7. Right. Let's do that. Okay, let's say this is 1, that is 2, 0, and negative 1. Same thing, 1, negative 1. Alright, now just try to put the point first. Inflection point, negative 0.4 and 1.3, so it's not very good, but this will be here. The minimum 0, 0, because I know it's minimum, so I can write below that. So local mean. Right there. And the local max 0.8. And 1.03. So if this point, and inflection point here. So first, the graph decreasing and concave up. So at that point, it will just change the shape a little bit, go to here, and then from that point, 0 to 0.8, and then from 0.8, it will just go down. And how far down? Well, if we have x equal to 2, this equal to 0. So in this case, actually we have this. Yeah. Oh. Sorry, the inflection point is negative 0.4. Should do this in pencil. Recommend you to do graph everything in pencil. Right. Negative 0.4 and 1.03, so the point had to be here. Okay. So and then when x equal to negative 1, of course we have the function already. If we trace when x equal to negative 1, the graph is 3, so it's way up there. Sorry, that's very bad graph, but let's say it's about here. Oh, yeah. Yeah, so the graph like that. Of course, that's what we have, similar to the graph there. So we have the inflection point of negative 0.4 and 1.3. Right. So of course we put all of that information together from the first derivative, second derivative, put in the sign chart so we know the curve. Then fit the curves into the points and we have the graph. So that's all the example I want to do in this section. As always, thank you for watching. See you in another video in Calculus 1.